we're going to be introducing you guys to a new type of function today. You guys know polynomials are functions, rational expressions can be functions, exponentials can be functions, right? Well, integrals can be functions too. So I'm going to introduce you guys to the integral function. We'll learn what that is. We're going to start off by evaluating it. Evaluating means like you have a function, you plug a number in, you get an answer out, right? So we're going to do that. And then we're going to pull back some of this old stuff we learned about. Remember when we compared the graphs of f and f prime and its second derivative to talk about concavity, increasing, decreasing, relative extrema? We're going to pull that back, but we're going to be applying it to integral functions today. So let's go ahead and jump in here. All right, so the graph at the right is a graph of f, okay? But I'm going to give you guys a new function called g, and g is an integral function. This is an integral function. It's a function that is basically an integral. And you'll notice that the x, the input, where does it go? Right there. Now this variable actually doesn't matter, so I don't want you to focus on those ones. A lot of times they can use different variables, and you'll see why. It doesn't matter what those are. But for this function, what matters is what's here. That's your x. That's where the x is at. And so every function has an x where you plug numbers into it, right? And an integral function, that's where the x would be. So what we're going to do is we're going to find g of negative x, g of negative 4, and so on. We're going to put it in a table, and we're going to graph the result. Now, so before you think, well, why would we graph it? We have the graph right there. Remember, that's a graph of f. We want to graph g, which is an integral of f. Okay, so that's our goal. So I'm going to show you guys how to do this really quick. I'm going to make some workspace here for me, and you guys can go ahead and do this as well. Okay, so first of all, here's my integral function right here, and I want to find what is g of negative 6. So the first thing I'm going to do is I'm going to plug in negative 6 here and here. Okay? These x's, I wish I hadn't used x's now in retrospect. I wish I would have used t's. So if you want, you can actually just change them now. Because I don't want you guys to think, oh, there's x's, so I should plug in the negative 6 there as well. You don't. So there's that. Now, let's go ahead and do this. So I want to figure out what does this equal. So if I want to know what this equals, I need to figure out what this equals. Yeah? Yes. So, how do I do this? The first thing we have to do is when you do an integral, you should have the smaller number on the bottom, right? And we don't. So I'm going to reverse that, which I'm allowed to do so long as I put a negative in front. Now to get the rest of it, we just need to understand this means area under the curve, right? So what's the area under the curve from x equals negative 6 to x equals 0? So that's going to be 2 times 1 is 2, cut in half is 1. 4 times 2 is 8, cut in half is 4, but it's under, so it's negative, right? So we have 1 plus a negative 4 by putting those areas together, right? Which ends up giving me what is a final answer here? Inside is negative 3, right? But there's the negative on the outside, which comes out to be positive. So that's the answer for g of negative 6. G of negative 6 is 3. Yep.
So in order to split the numbers you start off with in your integral, like what do you have to do? Like what do you make negative again?
So you only have to flip it if the bottom one is bigger than the top. So 0 is bigger than negative 6, so we wanted to reverse that. And when you do that, you just put a negative in front of your integral. Okay. All right, let's do another one. So I'm going to let you guys walk me through this one a little bit, and then I'll let you guys do the rest after that on your own. So first of all, we're going to start off not with Roxanne because she's not here, but we'll start off with Brandon. So Brandon, I want to find g of -4 next, I guess. So what do I write here?
-4 on top.
Mm-hmm.
0 at the bottom.
Okay. And then it's f of t, d of t, right? We would have to flip it. And why do we have to flip it, Brandon?
Because the smaller number has to be on the bottom.
Good. So that would be 0 on the top, -4 here. And when we flip it, we don't want to forget to put a negative in the front, right? Juliana, what's next? Good. And we're going from 0 to -4, or -4 to 0, I mean. So that's from here, -4, to here. So that area, we've already done it. It's -4, so the final answer is 4. Okay, so that's that. So I'm going to let you guys do the rest here. Before we begin, though, let's do 0 together also. But you guys should be able to tell me what the answer to that is pretty quickly. It's 0. Because if you plug in 0, if you're going from 0 to 0, we have a property that tells us that means no area. It's just 0. So let's go ahead and do the next one. I'll split the class up. We'll let you guys do different things. So can I have these two rows? Can you guys calculate g of 2 for me? And then you two rows here, can you guys do g of 4? And then last guys over here, you guys can do g of 6, okay?
G of 6.
That's right. Take a moment. Figure it out. For 2, -2 is correct. Dario, what'd you get for 4? 0 is correct. And then Andy, what'd you get for 6? 4. Okay, so guys, let's get our bearings here once again. So g is an integral function where you're taking the integral of the graph that we have up here, which is f. Integral just means area under the curve, right? So what's happening here is I'm showing you what's happening to the area under the curve as x is changing. Well, the area starts off at x equals -6 to be a +3. So the area is 3 at this point. But by the time we get to -4, the area has increased to 4. Now, let's think about why that makes sense. Why would the area increase as I go from -6 to 4? Well, that's because, look, where's my area located? Above. So we're adding area at that point, right? So my area should be going up at that point, right? And then from then my next point, by the time I get to 0, my area is nothing anymore, so it decreased. And why did it decrease? Because my area was below the x-axis at that point, so we're losing area now. And to continue that process, as we move on, what should be happening? Will it be decreasing or increasing? Decreasing again, because it's still below. And sure enough, by the time at x equals 2, we're even farther below the x-axis. So now we have a negative area that we're working with because it decreased so much. And then finally, after that, we're above the x-axis again. But the amount of area that's above matches the area that's below. So that puts us right back to 0 at that point, right? And that's why we got 4, 0. And then after that, you're just adding area of 4. So at the very end, we're at 6, 4, which is here. So there you go. So this is an integral function, okay? An integral function is a function that has an integral in it. And what it represents is how the area under the curve of its integrand is changing as x is changing. And likewise, you can graph the integral function as well and kind of see some comparisons. So in other words, the slope of this function is going up because that's a positive area. Or in other words, because it's above the x-axis, and that should sound a little familiar from chapter 5. Remember that? Positive slope means above the x-axis. Negative slope means below the x-axis, right? Those are some old ideas there, but we're looking at them from the perspective of integral functions now. So there's that. So what is an integral function? There it is. It's called an area accumulation function. Okay? because basically you're accumulating area as x goes on. Now, I'm going to introduce you guys to what seems to be a really strange rule. It's strange because how you do it is stupidly easy, and it's ridiculous, yet the concepts behind it are pretty deep and rich. So it's worth looking at. So I'm going to introduce you guys to something called the second fundamental theorem of calculus. Okay? Here's my integral function. I'm going to give you this integral function. It says use the first fundamental theorem of calculus. That's the thing where you integrate it, plug in b and a, and subtract them. So they want us to do that to rewrite this as a normal equation without an integral in it. So here we go. G of x is equal to the integral from 0 to x of 2t dt. So first of all, let's go ahead and do the integral. What is the integral of 2t? T squared. And we're going from 0 to x. So if I plug in x, I get x squared, right? And then if I plug in 0 and subtract that, I get 0, right? So there it is. So this function is the same thing as this function. It's just that this one's written as an integral, and this one's just written as a polynomial, but they're actually the same function. All right. Now, number 2 says, use your answer from part 1 to find g prime. So what is g prime then? If g of x equals x squared minus 0, what's g prime? It's 2x. Now, a couple of things I want you guys to notice. This is pretty much the same thing as that, right? And that should make sense. Because isn't a derivative the opposite of an integral? So if we integrate it, and then we take the derivative of it, wouldn't that just take us back to what we integrated in the first place? That makes sense. But notice there's a difference, right? It's not t anymore, it's x. And that's why I told you in the last slide, it doesn't really matter what variable's there, because with an integral function, that variable kind of goes away, technically, when you do the first fundamental theorem of calculus. So, that's it. That's the takeaway. So here's the second fundamental theorem of calculus for you. But this has to be a constant, okay? It has to be a number down here. Speaking of, what happened to my constant when I took the derivative? On the last page, what happened to that 0? We just kind of got rid of it, right? And even if it wasn't a 0, like let's say that it was like a 1 or something like that, it would still go away, right? Because when you take a derivative, doesn't the constant go away? So it doesn't matter what this is down here so long as it's a constant, okay? Some number. If g of x is equal to this integral function where you have an x on the top and a constant on the bottom, then the derivative is just going to be the original integrand, but with an x instead. So it's really lame in the process. The idea is rich. We've covered a lot of cool ideas there, but now let's look at the process. So if I give you something like this, and I say find the derivative of it, it's just this with an x in it instead. Okay? So that's it. It's really simple. Let me show you guys. Let's go ahead and take a look at example 1. All right. Using the second fundamental theorem of calculus, find f prime of x. All right, so do I have a constant down here?
Yes.
Yeah, and just an x up here, right? If you have just a constant down there and an x up there, then the derivative of this function will be just what you see right there, but with an x instead of a t. That's it. Okay? So that's simple. But it only works if this is a constant and this is just an x. Now tomorrow we're gonna mess with these a little bit, and you'll see some changes that causes. But not tomorrow, Thursday. But if it's 1 and x, then this is how you do it. Let's do another one. So, do I have just an x up here? And just a constant here? So what's my derivative?
Negative e to the x plus.
Yep, same thing as we have here, but just with an x instead. Okay? Weird? There it is. All right, so I'm sure you guys will be fine with this, but I want to let you guys practice it anyway just to make sure we're good. See if you have any questions. So I'll throw a couple here at you. Go ahead and try student practice 1 there. Just sit down.
That's like that.
Nathan, what did you get for number 1 here, bud?
X squared plus 4
Good. And how's about Dylan? What'd you get for the next one? Okay, so there you guys go. Pretty sweet. Second fundamental theorem of calculus. Okay, so now you guys remember. Let's review some stuff from a while ago. Hold on. Math. Stuff from a while ago here. We have. You guys remember that if g of x, a function, is increasing, what does that tell us about its slope? It's positive, right? And if a function is decreasing, then its slope, its derivative, is negative. And if you go from increasing to decreasing, that gives you a relative max, or from decreasing to increasing. Let's add something to our notes, though. Let's go ahead and put undefined here as well, because it could be 0 or undefined. The derivative could be 0 or undefined. Okay? All right, so now, what's this got to do with our topic today, which is integral functions? Well, what is g prime of x? It's f of x. So this is f of x for the integral function. So in other words, anywhere where f is positive, g would be increasing. Or anywhere where f is negative, g would be decreasing. Okay? So we're pulling back this old concept, but we're doing it from the perspective of integral functions. All right? Or also, if f of x is undefined or equal to 0, and it changes signs, well, that would be a relative max, and so on and so forth. All right, so let's put it to work here. The graph at the right is a graph of f of x. Once again, I'm using the same graph for everything today. And g of x, which I do not have a graph of, but g of x is an integral of that function over there. Which means that g of x is basically just the area under the curve starting from 0. So now, where is the graph of g increasing? So follow along with me and write this down with me. G is increasing when g prime, g is increasing when g prime is what? Positive. Now I'm going to throw something in here though really quick that you might not have thought to do. G is increasing when g prime, which equals f, don't you guys agree? If this is g, then doesn't g prime equal f? Second fundamental theorem of calculus? Okay. So g is increasing when g prime, which is f, is positive, right? Where does that happen up there? Where is that graph of f, which is g prime, where is the graph of f positive? -6 to 2. Wait. -6 to what? Good. So from here to here, f is positive. Don't you guys agree? It's above the x-axis. So if f is positive, that means g prime is positive. If g prime is positive, that means g has a positive slope, which means it is increasing, right? So there's one interval. Now, is f positive here at -6? Yes. Is it positive here at 4? No, it's 0. So I'm going to put a bracket here, or a parenthesis. Okay? Where else is f positive? 2, you could say, so it is positive 2 to 4. We want to be as inclusive as we can. So we're going to go from 2 to 8. Is 8 going to be a bracket or parenthesis? Okay, because it's actually above the x-axis, right? 2 is a parenthesis because it's on the x-axis. All right, so there you go. So where is g increasing? G is increasing when its derivative, which is f, represented by this graph above, is positive, and that happens here and over here. Okay, let's do another one here. Where is the graph of g decreasing? And so, number 2. G is decreasing when what? Which equals F is negative. And where does that happen? Parenthesis or bracket? There you go. Because it's below the x-axis from here to here, not including the endpoints. All right. Where are the relative extrema? -4 and 2. Good job. Okay, so let's review. So, well, I'll do this one. Let's say number 3. G has a relative max when G prime, which is F, goes from positive to negative. And where does that happen? Where does the graph of F go from a positive value above the x-axis to a negative value below the x-axis? There you go.
So like an arrow down, but where the line hits the x-axis of 0.
Yep, absolutely. So just basic, so when you're looking for relative extrema, look for where it touches the x-axis, basically, right? Now, we got to do the other one over there, too. This one is going from below to above. In other words, negative to positive. That makes it a what? That makes it a relative minimum. So we'll write that also. So G has a relative min. Hello. When G prime, which is F, goes from what to what? Which is at what? There you go. All right, so that's the example. I'm going to put up a student practice for you guys. Can I erase my words? Take that as a yes. All right, there you guys go. So when I call on you, I'd like you to share out your answer, but like in a sentence format, okay? So I'm going to use my cards first, but I will come to you, Jen, if I need you. Zachariah, where is the graph of G increasing?
The graph of G is increasing. -5 to 2.
Say that again, from negative what?
-5 to 2. Or wait, no. -5 to -2.
No, what you just told me is where F is increasing, but I want to know where G is increasing. So I'm going to let Jennifer help me out with that. Go ahead, Jen.
G is increasing when G prime equals F is positive. Parentheses -2 to infinity.
You got it. So anywhere where that graph is above the x-axis, which is from -2 to infinity. Good. All right, next one we're going to try Alyssa. What did you get for the next one?
G is decreasing when G prime of F is negative at -2.
Yeah, very good. So the answer for part B is negative infinity to -2 because G is decreasing when G prime, which is F, is negative. In other words, below the x-axis. Yeah.
So if you use infinity, would it be parentheses?
Yeah, infinities are in parentheses. Angie, where are the relative extrema and explain? Explain.
G has a relative minimum when G prime equals F goes from negative to positive at x equals 2.
Beautiful. All right. That is perfectly worded. All right. So here we have a relative minimum because G has a relative minimum when G prime, which is F, this graph, goes from negative below the x-axis to positive above the x-axis. So relative minimum. All right, so let's move on to our next part here. We're going to do the same thing, but now instead of looking at increasing, decreasing, and relative extrema, we're going to look at concavity and points of inflection. All right? So, pay attention. Here we go. When G is concave up, we know that its second derivative is positive, right? Remember that? Concave up looks like this. G is concave down when its second derivative is negative. G has a point of inflection where the concavity changes, and that means that the slope of that point would be 0. Or, yeah, the second derivative at that point would equal 0. Okay? All right. So, but we don't want to think just in terms of G double prime, because to get to G prime, what do we have to look at first? We got to look at G prime first. So if you want to get to G double prime, you got to look at G prime first. Now G prime equals what? And therefore G double prime is what? So here's a sentence for us then, in other words. So the concavity of G, can be seen by observing the slope of F. So the concavity of G can be seen by observing the slope of F. Okay? So if G prime, which is F, is increasing, that would mean it has a positive slope, right? Or if G prime is decreasing, that means F is decreasing, and if F is decreasing, that means it has a negative slope. Or if G prime changes from decreasing to increasing or increasing to decreasing, then at those points, that's when the concavity would be changing. Okay? All right. Clear?
Or
Here we go. The graph at the right is a graph of F, which is G integral G, and G of x is equal to the integral of f of x from 0 to x, right? So that, let's write this first. G prime is equal to what? F of x. And G double prime is equal to f prime of x. So in other words, the concavity of G can be observed by looking at the slope of f. So by last time, in the last set of problems, we were looking at whether this function over here was above the x-axis or below. We're not looking at that this time. This time we're looking at the slope of this function. The slope of this function will tell me about the concavity of G. All right, so here we go. Where is the graph of G concave up? Well, here we go. Part A, G is concave up when G double prime, which equals what? F prime, is positive. Where is f prime positive? Where is the slope of that graph positive? 0 to 4. Good job. 0 to 4.
Oh wait, never mind.
these points.
On your notes, you might want, I wouldn't include this in your answer, you know, like an FRQ or anything, because technically, and some of you guys have been doing this on like your FRQ tests and stuff, like, because that's how I teach it, so I understand, but you can't do that. So make sure you always write the way I tell you to write it when I show you FRQ examples and stuff. You can't call it the slope of f. F prime, you don't want to call it the slope of f because derivatives tell you slopes at specific points, yes, but it's not the slope of f. There is no slope of f. It's changing constantly. So you don't want to use that word in calculus. We want to say derivative. So, but to help our minds, Yeah, you could say that. That would be fine. Huh? Yeah, if you're talking about a specific point, right? But we're talking about an interval, right? So you could say the instantaneous rate of change or the instantaneous slope is always positive on this interval. You could say that. I think that would be okay. But just to keep things short, sweet, and simple and always the same, I would just stick with saying derivative and stuff like that in your FRQs. I wouldn't put the word slope in there necessarily. That's just me using simple language to help you guys grasp the concept, but proper expression, we should probably use the more formal language, right? So anyway, so there's that. Let's go ahead and move on to part B. Part B, we're looking for where G is concave down. So G is concave down when what? Good job, guys. Is negative. And where does that happen? Where is F prime? And what does F prime represent in our minds? The slope of F. Where is the slope of F negative? Negative 6 to 0. Good job. Okay? No, because we don't know what the slope is at this point at a cusp. There is no slope. So I can't say the slope is negative here or positive because it instantaneously changes there. Oh, negative 6? That's a good question. Possibly. Yeah, for this, we just, like, so the one-sided slope, I would say definitely is positive. So I don't, just so you guys know, on the test, they've told me they don't take points off for brackets versus parentheses, but I try to teach it as close as I can to correct. But I think you can get credit either way with this one. All right. You have a question? You just yeah.
So is it a parentheses or a bracket?
So for the negative 6, I'm saying it just doesn't matter. Because technically, yes, you could argue this point has a positive slope, but we don't really know what's going on the other side because they didn't give it to us. So you can use bracket or parentheses, it doesn't matter. But this guy, you definitely couldn't use a bracket because there is no slope at that point. It's a cusp. And remember, I'm using informal language. I should say there's no derivative at that point, right? All right, let's go ahead and do C here. Where are the points of inflection? So I'm a little conflicted on this answer, but let's answer it real quick. C. G has a point of inflection when G double prime, which equals F prime, what? Is 0? Or maybe that's the part I'm a little conflicted on. The good news is I never see them ask questions about this sort of stuff on the AP exam, and I've been looking all over different textbooks and I can't get a straight answer on it, so I don't know. But let's put it this way: where G double prime equals F prime changes signs, so it definitely has to change signs. I'll tell you that much. It has to change signs. It has to go from positive to negative or from negative to positive. G double prime, which is F prime, changes sign. So G double prime is the answer to your question. So let's back up. Ready? G has a point of inflection when G double prime, the concavity, changes signs, right? Because that's when you go from concave up to concave down or vice versa. And that point where they connect is a point of inflection. So where does G prime, which is F prime, which is the slope of F, where does that change signs at? Kinda. Try again. X values. 0. Now here's my one place where I'm a little bit conflicted. I've heard it said in some books where they say that a point of inflection, G double prime has to equal 0. The problem is here, G double prime, which is F prime, which is the slope of F, actually doesn't equal 0 though. The slope at that point is undefined. It's 0. Or I mean it's undefined. So that's no good. Technically, and like I said, I've looked at all the FRQs I could find in the past like 15 years. I've never seen them give something ambiguous like this, so you don't have to worry about it. But I have seen them do things like this where it's smooth. Now, if it's smooth, now the slope equals 0 and the slope is changing, right? But a cusp, I'm a little confused on, honestly. For now, I just want to write it like that, though, and we'll go with it. All right, so that's it. I'm going to let you guys practice that a little bit, and then we'll call it a day.
Let's go.
Let's go. I'm not going to do the explanations because we don't have time, but from negative infinity to negative 1, as well as from 1 to infinity, is all concave up. But there are no places where this graph would be concave down. And therefore, there is no point of inflection either. If it doesn't change concavity from positive to negative, then there can't be a point of inflection. All right? So that's that.
What's Mr. Daly?